Presumably you are all here for thermodynamics, introduction for thermodynamics. It is a pretty full class. It won't actually fill up the lecture hall because the lecture hall I think holds over 300, but I think there is about 200, almost 250 of you enrolled. Most of you should be mechanical engineering majors or aerospace engineering majors, but I'm sure there are a few others, for example, from environmental engineering, who also have to take this class. I just pulled this up from the EEE website, so I can go quickly over a couple of these items. The first thing, I guess you all know how to get here, so we don't need to talk about that. The class has 2 teaching assistants, and they're both named there, Franz and Doreen. Franz is here, but Doreen is not. But you'll get to see her this Friday when you go to the first discussion section. So this Friday we'll start with discussion sections. You go to the bottom where it says information, a couple of things I want you to be aware of. You need to enroll through the Distance Learning Center. And I think if most of you took dynamics, how many of you took dynamics from Professor Jabari? So you are already familiar with the system through the Distance Learning Center. I won't use it as extensively as he does, but I will use it to collect homework. So do not turn in any homework in the boxes in the Engineering Gateway building, because your homework, if you turn it in there, will stay there for the whole quarter and nobody will ever see it. So the way you will turn in your homework is once you enroll in the class in MAE 91 at the Distance Learning Center, then you can upload your homework by the deadline as a PDF file into that website. I'll go a little bit into the details in a moment. So that's number 1 item that is important. The second one item that is important is that you'll need an iClicker. So if you don't yet have an iClicker, you need to get one from the bookstore. We will use the iClicker to do a couple of, to achieve a couple of goals. One is participation, so just showing up will get you a few miscellaneous points, but also quizzes via the iClicker. And so we won't start doing that until next week, so make sure you get an iClicker before you come back to the lecture next week. Let's see, what else do I have here? The text, a few of you have already asked questions about the text. We're using the 8th edition, which looks like this, at least the hard copy version of it. So, and this is a brand new edition. I think it actually has a copyright of 2013. And this is the one we're using. The publisher told me that maybe there weren't as many in the bookstore. So if you go to this link that is on the EEE website, there are 2 links there. The first one just takes you to a place where you can buy the book directly from the publisher. And the second one, which perhaps is more important for you now, you can actually download the first 3 chapters. So if you don't have the text yet, you can get the first 3 chapters from that second link. And the first 3 chapters will carry you probably about at least 3 weeks into the course. We're roughly going about a chapter a week, except there are a couple of chapters that are long and will take more than a week to cover them. But you can get the first 3 chapters for free from this link right here, the second link right here. Okay. Let me go a little bit into the syllabus, which is also there. First part, I guess, is not important. You may have seen this already, so you know how the course is graded. It's heavily graded on exams. As you can see, the last 2 entries, 40% and 45% are the midterm and the final, respectively. But there are miscellaneous points on the homework, 10%, and participation, which I described a moment ago, which is 5%. You also have the dates for the midterm and the final there, so make sure you are going to be around those dates. The homework doesn't really count as much. 10% is not really a whole lot, considering the amount of time that you will probably spend on the homework. So I want to warn you about a couple of things. The idea of the homework really, in addition to that 10%, which is really pretty much like a token number of points, is for you to practice. So make sure that that's what you're getting out of doing the homework. Practicing on the homework problems will prepare you for the exams. And that's the main goal, more than the 10%. If you just copy, and every year students do copy, if you copy and you don't practice, you will get maybe close to the 10%, but you'll do really bad on the exams because you won't have developed that practice. So keep that in mind. You can certainly collaborate. You can work on the homework in groups as long as you know yourself that you are actually thinking and putting the time to learn and solve the problems. Yes?
Are you going to have a course book on reserve on the library?
I will do that. Yeah, thank you for reminding me. Can you make a note of that? We need to put a book on the reserve. And usually I just do the shortest period. I forget which one it is, 2 hours or whatever the shortest period is. Another thing that is very important is that we don't take any late homework. So the homework is due at a certain time, as again, via upload. You have to upload it by the deadline. If you don't, that's it. Don't come back saying that whatever excuse you have for that day, we won't take any late homework. You will do have the benefit at the end of the course. We usually drop your worst score, so if you happen to miss one, then you don't get heavily penalized. Make sure you know the policy on academic dishonesty. You can read on it. There is a link on the main website for the campus academic dishonesty information. Best thing is just to be honest. If you're honest, then you won't have any problems. As far as the content, here's the content broken down into weeks. Actually, a subject and then the amount of time that we're going to spend on each topic. It should add up to, 2 lectures per week, 10 weeks, so 20 weeks. 20 lectures. And you can see the breakdown there. So whatever you see 2 lectures, that's 1 full week. So we'll spend the first week in item number 1, which is introduction and some preliminary concepts. And then keep moving along. The main 2 items in an introduction to thermodynamics course are the first law of thermodynamics and the second law of thermodynamics. So we'll spend about half of the course developing material that has to do with the first law of thermodynamics, and then the second half of the course with material that has to do with the second law of thermodynamics. Already told you about the text. The last page here just tells you how to do your homework. The main thing, again, is that you submit it as a PDF file. So whichever way you do it and whichever way you get it into a digital format, make sure you convert it to a PDF file before you upload it. The rest of the items there are fairly straightforward. You don't need to copy the statement from the text. Just go ahead and start solving the problem. Do it in an organized manner so the person who is grading your homework doesn't have to guess what you're doing. So you list your unknowns. If it's useful, draw. Some problems are very simple, especially at the beginning, that you don't need to draw a schematic. But later on, as the problems get a little bit more complicated, we want you to draw a schematic or a sketch of the problem that you're solving. List your assumptions. Write everything down, all your equations. so that they can be understood. And any important answer, just put it in a box. It takes a lot of time to grade 250 problem sets, so that's the reason really for all of these details. Okay, I think that's all I have here. Does anybody have any questions about any of these? No questions? Okay, yes?
So is the homework coming from the book?
Yes, in fact, let me go back here. The next link, homework assignment. If you go here, you can actually see all of the problems for the whole quarter. All right? So you'll see there are a total of 8 assignments, homework assignment 1 through homework assignment 8. They all come from the book, and so the problem numbers for the first week are these ones here. You also have a reading assignment, which usually just goes parallel to my lectures. The first week, it is chapter 1, and so on. And again, these are the problems from this 8th edition. A common question from the students is, can I use the 7th edition, or can I use the 6th edition, and so on? The answer is a cautious yes. You may use an earlier edition because the material is probably 95% the same. What happens from edition to edition is that some of the stuff gets shifted around, chapters get recombined, and that has happened this time. So if you go by an old edition, the chapters won't match exactly. And also the problem numbers won't match. So you got to do these numbers from the 8th edition. If you turn in the problem numbers from an old edition, they'll be the wrong problems. So that's the only thing you have to be careful about. So yes, you can, with that caution, and it is your responsibility to make sure that you're doing the right problems. That's all. Don't ask me or the TAs, which ones are the problems in the old edition. You have to find that out on your own. All right. Any other questions? Yes.
If we have one of those distant learning center accounts from
yes.
last year,
Yes.
do we need to re-enroll?
You need to enroll in MAE 91. So once you go to the distance learning center, just look for this class.
Last year.
I'm sorry?
Like if you were retaking this class?
You have to enroll in the new one.
Okay.
It's a different website. So you probably see still somewhere there the old one from last year, but make sure you enroll in this year's. I'm sorry to hear that. Are you taking it again? I hope it wasn't my fault. All right. Okay. Let's see. Let me start by, let me make sure this is working before I do anything else. All right. It seems kind of dark. Let's put a piece of paper here. Oh. All right, so we may have to, is that readable or is the glare a little, let's see. Okay, that's not bad. I'll come back to that. Let me start by showing you a video. And we're not going to see the whole video, but at least a portion of it. Okay, we don't need to watch the whole thing. It's on YouTube, so if you want to watch the complete video, you can just go to YouTube and type jet engine, and you'll come up with not only this one, but many other videos that have to do with jet engines. And I just picked this as an example of a device that is obviously heavily based on thermodynamics. And in the course of watching that video, you actually heard many of the terms that we're going to be working with as we go along in the course. The engine itself, it's obviously an important aspect of thermodynamics, but you also heard about compressors, combustion chambers, nozzles, turbines, and by the time we're done 10 weeks from now, those words should be very familiar to you, and you should be able to know what the thermodynamic principles that control those devices. Now, really, to get to something like that, to understanding everything about a jet engine, particularly if you're an aerospace engineering major, obviously it's not just the thermodynamics. This course really is the first in a series of courses that guide you through the process of understanding how something like a jet engine works. There is not only the thermodynamics, but clearly there is a lot of fluid mechanics. You hear about the gas, the air coming in, the combustion process, the combustion gases, the combustion products coming out. There is a lot of fluid mechanics in there. There is a lot of heat transfer. So these are, not surprisingly, the names of courses in your program of study as you go along. And then, of course, if you're an aerospace engineering major, then there is a course on propulsion, where perhaps you are finally able to put some of these fundamental ideas together. Now, thermodynamics is not just for aerospace engineers. Obviously, it's extremely important for mechanical engineers as well. What do you think of when you see the word thermodynamics? What comes to your mind? If you were to do a quick word association, what word comes up right there?
Rocket engines.
Rocket engines.
Energy.
Energy? Heat. That's one usually that comes up quite often. Any of those answers are obviously correct. The word heat is a common one. Somebody else has said energy. More important perhaps than just energy itself is energy transformation. How do we change energy from one form to another form? Thermodynamics will help us with that. Interestingly enough, the word dynamics is associated with what? Huh? Well, a little bit more narrow than just physics. Say that again? Movement, right? In particular, what about the difference between kinematics and dynamics? Kinematics is also movement. Well, in physics, what's the difference when you talk about kinematics versus dynamics? In dynamics, what's that word? Somebody said here. Who said forces? She said forces. In dynamics, usually you pay attention to the forces that cause that motion. In kinematics, you only want to quantify the motion itself. So I always say that this thermodynamics is a little bit of a misnomer, at least for the type of thermodynamics that we're going to be looking at, because it's really closer to what you would call thermostatics, which doesn't exist, at least as a basic course. Because as you will see as we go along, we're really not going to be paying too much attention to how processes occur or how things change during that motion, but actually more about before and after. We will pay some attention to the during, but most of the thermodynamics that you see in an introductory course like this is like, this is how things were at the beginning and this is how things are at the end of a certain process. And then we're trying to make some calculations to see maybe how energy was converted. Let me ask you another question. Can you hear me well back there? Because I can speak a little louder. And if it doesn't work, I can wear another microphone. It's just that it's going to keep putting burdens on me. Let me know if at any time during the lecture you're having a hard time hearing way back there. You can also move closer. There is plenty of space here near the front. Let me continue with this. One important aspect, of course, of our study of thermodynamics is based on an important conservation law. from physics, which is conservation of energy. For us, energy is a quantity that is conserved. We're not talking about any relativistic effects of thermodynamics where energy could be converted to mass and vice versa. For us, energy is a conserved quantity, and so, of course, is mass. All right, so when we talk about energy, we obviously think of different forms of energy, and part of understanding thermodynamics is understanding that conversion process. How do I go from, say, having chemical energy into having at least a portion of that chemical energy converted to mechanical energy? The concept of heat itself by itself is important. We're going to be looking at systems that transform energy, that energy conversion process. So here I list some examples. A power plant. If you're a mechanical engineer, then a power plant perhaps is more of a common device for you than, say, the heat engine, the jet engine that we were looking at in the video. Refrigeration systems designed to move heat around, right? To move energy in the form of, say, temperature, heat, from one place to another. The internal combustion engine, which operates in your cars. Fuel cells, also devices that convert energy in one way to another. We just saw an example of turbines. I'm just throwing words here down. I could add, of course, a few more, but just so that you can get a little bit of an idea. And of course, the rocket engine that we saw in the video. So as I said, the video was just one example, but here's another one. Here's a typical schematic of a power plant. What is this power plant doing for us?
Generating electricity.
Generating electricity. Right? And you see that here. Right? Of course, this is a simple schematic, so it's represented by this one electric generator that produces electricity. Where does the generator get the energy from? The turbine. So there are several things happening here at the same time. Let's just, and of course you see many of the components of a typical power plant. There is a boiler here, the turbine that I just mentioned. There might be pumps. In this case, we're just representing all of the pumps by one. There is a condenser right here, which is this rectangular box. And of course, there are some auxiliary systems, like some mechanism to cool the working fluid. In this case, they have a cooling tower, stack for the combustion products to go out. So, for example, if we just focus for a moment on this part, so where we have the boiler, the turbine, the condenser, and the pump, we can see that here on this other, which is just that part of the plant. Is not really that other one blown up. It's a different schematic, but you see the four components that I was just referring to. The boiler, in this case, called a combustor unit, the turbine, the condenser, and the pump. So one of the things that you see here that is very important in thermodynamics is that many of these processes that are important to us as engineers operate in cycles. So what you have here is a cycle. You can see here cycle working fluid. There is a fluid that is going around through each of these devices over and over and over and over and over again. In the case of a power plant, what is that fluid? Water. Right? Water is typically the fluid that would be what we call the working fluid in a power plant such as this one. Typically would be water. So what you have, pick any starting point. For example, let's pick this point here between the pump and the combustor unit. You're bringing that water as a liquid into that combustion unit. In that combustion unit, you have some sort of a high temperature source. Maybe you're burning something. As you can see here, we're feeding fuel and air, and of course producing a chemical reaction, and that chemical reaction will generate high temperatures. Those high temperature combustion products then bring that water into steam. So boil it and bring it into high temperature steam. So that's what comes out, if you follow that process through the combustion unit, then you come out with, say, steam, some high pressure, high temperature steam. Then you take that steam, run it through a turbine. Work is produced by that turbine. So the steam just goes through the turbine, moves the blades, and produce some sort of a rotating power output, which then will drive your electric generator. Now, as the steam goes through the turbine, it loses energy. So the pressure of that steam and the temperature too will drop, and it may come out still as vapor, but at a much lower pressure and temperature. And remember, we started by putting liquid into the combustion chamber, and we have a vapor here. So what we are missing to close the cycle is a condenser, where we can bring that steam that came out of the turbine back into liquid state by taking more energy out of it. How do we take more energy out of it? We have another water system, which is the cooling water, that is coming in, removing energy from the steam so that it condenses. And then now I have a liquid, but I have another problem, which is that this liquid is at a pressure which is not high enough to be fed into the combustion chamber. That's why there is the fourth ingredient in the cycle devices is the pump. So now I need to take that liquid that comes out of the condenser at a low pressure and pump it up to a pressure that is high enough to go into the combustion unit. So you see combustion unit, turbine, condenser, and pump are the four main components of a power plant, such as this one. More examples. By the way, if you have any questions, just raise your hand, and I'll try to see your hand if it comes up and try to answer your question. Here's another example. What is this? Well, it's just a cylinder, right? And the crankshaft of an internal combustion engine. So here is the cylinder. This is another example of an engineering device where we need thermodynamics to understand how it operates. So what is happening here? Well, of course, we're putting fuel and air in. There's a spark to light it so that it burns. That high energy then pushes the piston down. The crank mechanism converts that linear displacement into rotation. So of course then we can drive the wheels by rotation. And then of course then the combustion products need to be exhausted through the exhaust valve. So that's another example. It's a completely different device from what we saw earlier in the power plant, but still, as you will see later, is governed by the same thermodynamic principles. And so suppose that I say, well, let me actually show you a little bit how this works. And we're going to see all of these things in detail later, but for the time being, I'm just going to show you some examples. This is what we call, so I'm going to take this cylinder and I'm going to flip it on its side like this for this next plot. So here it is. Down here is my schematic of the cylinder. So it's moving between this, the top of this piston is moving between this dash line and the lower dash line. We call this one the highest position, we call it top dead center. You may have seen that here. So the highest point of the top of the cylinder is called top dead center, whereas when it's all the way down at the bottom, we call it bottom dead center. So top dead center, bottom dead center. So this piston is just, in this schematic, is moving horizontally. But what I have done here, just to show you something of one of the things that we're going to be learning, is what we call an indicator diagram for this cylinder, for this internal combustion engine. And what we're doing is we're plotting pressure versus volume. And we're going to see lots of plots of pressure versus volume, temperature versus volume, and so on. So pressure on the vertical axis, volume on the horizontal axis. And of course, the volume is the volume in here to the left of this piston. So the minimum volume is the V sub C when the piston is at top dead center. And the maximum volume, of course, when the piston is at bottom dead center, is back here, the V sub A. And of course, as the piston moves up and down, then the volume, of course, changes between those two volumes. So take, for example, the point that is denoted here by R. When we are at R, we have the piston at top dead center, right? So then, suppose now we withdraw the piston, we pull it out, and if we do that, of course, the volume increases, and if we open a valve, which is not sketched here, but if we were to open a valve to let air in, then that's what would happen between R and, say, B when we reach bottom dead center. And now say we close the valves, and then we start pushing the piston back towards top dead center. Since we close the valves, now we have a restricted a volume that is decreasing. There is no escape for the air that is in here. Then it's obvious that its pressure will, I'm sorry, I shouldn't have told you B. We're going from R to A, right? So when we're withdrawing the piston, we're going from R to A. And now from A, we're pushing it back in. The valves are closed. It's not surprising that the pressure will start to go up because we're compressing that air. Then at some point here, which is maybe what is denoted here by C prime, maybe that's when the spark comes off. It ignites the mixture. So the pressure continues to rise. The volume continues to decrease. We reach top dead center. Still the pressure continues to go up, and then we reach a point Z there where the pressure is the maximum. At some point, we would have to then open the exhaust valves, and then, of course, notice that what is happening here is that the piston is already going back, between C and Z. We're already starting to go back. That's the driving part of the process. That's when we're pushing the piston back with the force produced by the combustion products, by the explosion of the mixture. And we go back to B. And then at some point, then we have to open the exhaust valve, and then the piston goes back and pushes all the combustion products out. So if we started at R, going first to A, then to Z, then to B, and then back to R, we have completed a cycle. So that's a typical cycle of an internal combustion engine. Let's look at one more. Any questions? Let's look at one more, which is the one we saw in the video. So here is that, and this is not a great picture, but this is the jet engine that we saw in the video. So the air comes in from the left side. It goes through the compression, through the compressing part of the engine, which is this bluish, greenish area here. Once that air is at a sufficiently high pressure, then it goes into the combustion chamber, which you can see here. It burns, and then the combustion products go out through the turbine. And the turbine, of course, rotates. And in fact, it is the turbine which drives the compressor. So some of the work that is generated by the turbine has to be used to drive the compressor and a few other systems in the engine. And then the exhaust comes back out, and that's the end. Look, notice a big difference. There doesn't seem to be a cycle here because the air is coming here and then going out there. It's a little harder to visualize a cycle. But let's do another plot. I may have to move this back down here. There are this. You can see another cycle here. Let me go. Let me make this a little bigger. There are two lines, and if you can see the two different colors, there is a black one which is actually closed. That is a cycle from 1 to 2 to 3 to 4 and then back to 1. And then there is a blue one which has the same one but then goes to 2 prime instead of 2, goes to 3 prime, and then goes to 4 prime, but that one is not closed. That blue one is representative or more representative of the real situation. We're plotting here temperature versus entropy, which is a property we're going to talk about later in the course. So temperature versus entropy. Just to give you a different type of a plot instead of pressure versus volume, which we saw in the other one. So if we start at 1, then as we go, let's look at the black one first. As we go from 1 to 2, that would be the compression. Notice that there are 2 other lines here that are important. One is this one here at the bottom, this curve, which I denoted constant pressure. This is a constant pressure line. So any point along this line has the same pressure. And then there is a similar line here, which is also a constant pressure line. Any point on this line here has the same pressure. Obviously, this one here is higher than this one here. So you can see as we go from 1 to 2, we're going from the lower pressure to the high pressure from 1 to 2. So that's the compression. That's as we go, say, we go back here, from the inlet to just outside of the compressor. That would be 1 to 2. So 1 to 2 is what we call the ideal process, whereas 1 to 2 prime is more of the real process. Then we go from 2 to 3 would be in the combustion chamber. Whether it is from 2 to 3 or from 2 prime to 3 prime, well, that's the difference between ideal and real. But that process between 2 and 3 or between 2 prime and 3 prime would be during the combustion process. You can see how that happens at nearly constant pressure. In fact, for the black cycle, it is a constant pressure because we're following exactly that constant pressure line. For the real one, you can see there is a little bit of a decrease from 2 prime to 3 prime. We're not exactly following that pressure line, but we're dropping off a little bit. And then finally, from 3 to 4, we're going through an expansion. We're going now from the high pressure to the low pressure. That would be the process through which part of the engine? Sorry? No. Through the turbine, right? So as we go through the turbine, we drop in the pressure from 3 to 4 in the ideal scenario, or let me reduce this a little bit again, or from 3 prime to 4 prime in the real one. 3 to 4 in the ideal one, 3 prime to 4 prime in the ideal one. Now, in the real engine, there is no going from 4 prime to 1 because the exhaust go out. You don't really bring the exhaust back out into the front. You just leave it there behind. But in the ideal cycle, when you first studied this type of a cycle for a heat engine, for a jet engine, you actually pretend that you're actually going from 4 to 1, and you close the cycle that way. This cycle is called a Brayton cycle, just so you know. This type of a cycle is a cycle for air, because the main substance, the main fluid that is going through is air. Sure, we're adding fuel at some point, But when we're talking about an ideal Brayton cycle, we're thinking of only the air, thinking what the air is doing. So the air is undergoing a compression, then a constant pressure process in the combustion chamber, an expansion through the turbine, and then somehow another compression, which in the real cycle doesn't exist. All right, so that's just another example. And maybe let's look at one more. This is, as you can see at the top there, a refrigeration cycle. So I'll move it up there. In a refrigeration cycle, such as the one that is operating in your standard household refrigerator, the idea, of course, is to take energy from some place and put it somewhere else. And of course, we do this in a refrigeration cycle. We're thinking of heat. So we're taking heat from somewhere and we're putting it somewhere else. And it also has 4 components or 4 devices that are important. And there are, of course, variations over this basic schematic. The 4 components, you can see them here: an evaporator, a compressor, a condenser, and an expansion valve. We already saw a compressor, even though it's a different type of a compressor, when we were looking at the jet engine a moment ago. So here's another compressor. We saw a condenser also. When did we see a condenser? When we were looking at the power plant. We saw a condenser there. So those we have seen, at least versions of them for a different equipment. The 2 new ones here would be the expansion valve and the evaporator. All right, so what is happening here? Again, let's start anywhere. Suppose we start here at number 1. It says here we're starting with saturated or superheated vapor. Those are keywords that we're going to learn about later. For the time being, just think vapor. We're starting with vapor. We put it to the compressor. So now the compressor increases the pressure. So when we come out 2, we have a higher pressure. It's still a vapor, but at a higher pressure. And then what happens? Then we go through a condenser. That's a key word for us. It means that this vapor is going to condense. So when it comes out at 3, it comes out as liquid. And of course, in order to do that, you will have to remove heat out of the fluid in the condenser. That's why you see here Q out is the heat that is leaving the fluid. What is the working fluid, by the way, in here? Some refrigerant. That's enough for now. We'll see about which refrigerants later, but some refrigerant, as opposed to water, which was the fluid in the power plant. So remove heat, leave the condenser now as a liquid, and then go through an expansion valve. Purpose of this valve is to drop the pressure. That's the main purpose of it. So it will drop the pressure from the high pressure in the condenser to the low pressure in the evaporator. So we come out at 4 at a low pressure. This was a liquid here. When it comes out, in that process of being throttled through the valve, some of it evaporates. So when it comes out at 4, some of it is liquid, some of it is vapor. And then we put it through the evaporator, and whatever remaining liquid there was will be evaporated. Obviously, in order to evaporate it, we need to add heat. And then we come out here where we started at. All right? So where is this heat coming from in your household refrigerator? From the inside. Right? This here would be the inside. Right? And where is this heat going out? Usually it's the back, right? But it's going into whatever room, right? Whatever room the refrigerator is located. So that's where that heat is going to. Are these the same, you think? So whatever heat I take out of the refrigerated compartment, is that the heat that goes down into the room? Why not?
It also includes heat that's a byproduct of the pump system.
Because you add some amount of work WC into it.
Right. If you look carefully, and again, this we haven't learned this yet, but there is a little magic part of the cycle that I didn't talk about here, and I need to drive the compressor. Right? The compressor doesn't run by itself; it needs to be driven, right? Which means essentially that it needs to be plugged in. Right? The refrigerator will need a source of energy, and that's also energy that is going into my entire system. So if I think of all of this as one device, so if I put all of these 4 components into a big black box, then I see that I am adding heat here, I'm adding something here. It's not heat initially, it doesn't look like heat, but it's energy, and I am putting it out. So if you just do a quick energy balance in your head, the conclusion is that this has to be larger than this because there was some other energy added here. Right? We'll learn that the details of this as we go along. Again, this is just to give you a sort of an idea of the type of devices that we're going to be looking at. But let's step back and go back to the basics. You've heard a lot of words today. And there's going to be a lot more. It will be important for you to understand the concepts very well. So we sort of have a system of definitions, and things may mean something in the outside world, but for us in thermodynamics, they have specific meanings. So let's go over a few of those. The first one is what we in thermodynamics call a system. And that's a very simple definition, as you can see there. A quantity of matter constitutes a system, which means, of course, that pretty much anything that you wish to study using thermodynamics is a system. Just pick a certain amount of mass and make that to be your system. We do something very simple in thermodynamics, which is once we define what the system is, everything else that exists, that is not what we chose to be the system, we just call it the surroundings. And so when we're learning thermodynamics, then the world is very simple. The world is the system that we're interested in, and the surroundings is everything else. And that's it. That's all we have to worry about. But then, of course, what is the dividing surface or line between your system and your surroundings? And we'll need a name. What do you propose we call it? Good for me. So we'll call it a boundary. So, the system boundary or the boundary will be what separates the system from the surroundings. Since most likely the system will occupy a certain volume, then the boundary will be a surface. Some sort of a surface that separates the system from the surroundings. Now, it is very important to understand that the boundary might be real, it might be a tangible surface, or it might be an abstract surface. So it might not really exist. Depending on the system that you're looking at, it might not be something that is really tangible, but you can define it. You will see that as we work on problems. Now, we can also call that surface the control surface. That's another name for the boundary, the control surface. If the system is closed, and we'll see what that means in a second, then we can call it a control mass too. What does that mean? That a system is closed and I call it a control mass. What do you think that means?
No mass transfer across the boundary.
No mass transfer across the boundary. So if the system is closed, is a controlled mass, and I put it right there in red, it means that no mass crosses the boundary. So a closed system is one for which no mass crosses the boundary. And therefore, the opposite, an open system, which, by the way, we can also call a controlled volume. An open system or a controlled volume is one in which mass is allowed to cross the boundary. All right? So are some of the preliminary concepts. There is another one that will come up once in a while, what we call an isolated system, and you can see the definition there. Nothing crosses the boundary. In particular, what do we mean when we say nothing? What's particularly important for us? Energy, right? We say nothing to make it very general. Nothing crosses the boundary. But really for us, in addition to mass as something that can cross the boundary, the other very important quantity that can cross the boundary is energy. So if there is no energy crossing the boundary, no mass crossing the boundary, essentially there is no interaction between that system and the surroundings, then that's an isolated system. You'll see that that's an important concept for us later as we start to develop some other concepts. Here is a very simple problem of which you're going to see a lot of. These type of problems are typical in thermodynamics. So the cylinder, for example, think of the internal combustion engine that we were just looking at a moment ago. So here's a cylinder. It's fitted with a piston. There is a gas in there. And there is a weight on top. And say that I can control that weight. If I control the weight, more or less weight, remove weight, add weight, I can move the piston up and down. So what do you think is the system here? Or one choice? One good choice for the system here. If I'm doing a thermodynamics problem involving something like this, what would you pick as your system? How about you? Right.
Sorry, what's the question?
Pick something. No, except for what is the question. You cannot pick that.
Inside the bomb.
What is the system?
What's inside the bomb?
Okay, but I want something more specific than that.
Closed.
I'm sorry?
Closed
Can't get that word.
system.
What?
Closed.
Oh, closed system. No, I want to know what the system is. Define the system for me.
The volume that the gas occupies in the cylinder?
I wouldn't use the word volume.
Mass.
The mass. That's a better choice. The mass of the gas. Or simply the gas. Take the gas as your system. Remember, a system is a quantity of matter. So it's really mass more than volume. Volume can change, right? Whereas the mass won't, if it's a closed system, right? If I don't let any of the gas escape. So let's say that we say the gas is our system, whatever gas is there. Then, of course, you see a dashed line there, which is the boundary, the control surface. You might argue, well, that's not very precise because I see some of the gas outside that boundary. Well, yeah, that's because that's a schematic, right? Ideally, you would like to draw that boundary so that it contains all of the dots that represent the gas. But you get the point. So if you pick the gas to be your system, then, of course, you would think that maybe the inner lining of that cylinder and the bottom surface of the piston constitute your boundary. But in a simple schematic like this, we just draw a dashed line like that. And that's usually sufficient. So, so now somebody said something about a closed system. Is this a closed system? It appears to be that way. I don't see any way for the gas to go out, assuming that this is properly sealed, that there's no gas escaping. Of course, if some gas does leave that cylinder, then it'll become a question what my system is. So suppose, in fact, let me go over that very quickly. Suppose I say that the system is the gas. The system is this gas. But now there is a leak, and maybe some of this gas is escaping here. Is that a closed system or an open system? Open, open, open. Anybody closed? Nobody closed? So here's one of the situations where you have to be careful. Suppose I say the system is the gas that was initially in the cylinder. And some of the gas escapes. Open or closed? You still think it's open? Huh?
It's closed.
Now he thinks it's closed. Why?
Because even if there is the leak, the system will still continue to work.
The system, the way I worded it, is the gas that was initially in the cylinder. It doesn't matter where the gas goes after. If
Volume inside is still the same.
well, the piston could be moving up and down, so the volume could change. The volume is not that important for this particular discussion. But if the system is all of the gas that is initially in the cylinder, it doesn't matter if it escapes. As it escapes, it's still part of my system. It just happens to be a very complicated system now, because where do I put the boundary if some of the gas has escaped? So I could treat this either way. I could say that the system is the gas that is in the cylinder at any time, in which case I might treat it as an open system with some of the mass crossing the boundary, or I can continue to think of the entire gas, regardless of what it is, as my system, and that's then a closed system. Some of those distinctions become important when you're solving problems, when you have to make that decision. This, of course, is a very simple problem, but in some problems you'll have to make that decision as to what exactly is your system. So you will see how that's the first thing you have to do when you're solving a thermodynamics problem, is decide what your system is.
How would you define it? How would you define the system so that it's open? How would you change it?
Well, if I continue to say that the boundary is the same boundary that we had at the beginning, so if I say the boundary of the system is the inner lining of that cylinder and the bottom of the piston, that defines the boundary. Whatever is inside of it is in my system. That's an open system now, right? Because there is gas crossing through whatever is leaking. Any other questions? Okay, let's see, how are we doing here on time? Let me make a quick distinction between two ways of looking at thermodynamics. There are generally two ways to study thermodynamics. One is called classical thermodynamics, and the other one is called statistical thermodynamics. The one we're looking at is classical. So we're looking at what we know as classical thermodynamics. The main difference is this. In classical thermodynamics, we are taking what we call a macroscopic view of our systems. Whereas in statistical thermodynamics, we're talking about a microscopic view. So this is a very simple distinction, but it's one that I hope will be obvious to you. So in the macroscopic approach to thermodynamics, we are measuring and working with quantities or properties such as temperatures and pressures. So we say we have, in the previous schematic, we had the gas in the cylinder. I could certainly measure its temperature. I could certainly measure its pressure. And I'll be here on my left side in my macroscopic view, two properties that I could measure. Now, in reality, where are those properties that I measure in the macroscopic approach? Where are they coming from? You have the answer on the right-hand side. There's really atoms and molecules that are moving around. Right? What is pressure? If I measure the pressure, say that the air in this room is exerting on that wall, where's that pressure coming from?
The molecules of the air.
Molecules of the air that are hitting that wall. Okay? When I'm looking at macroscopic thermodynamics, I am not concerned with the details of what's going on with those molecules. I just take a measurement of pressure and that's what I need. Or I make a measurement of temperature and that's what I need. We know, of course, that in the microscopic approach, those are due to atomic and molecular, and in the case of solids, lattices that are vibrating and so on, that are producing those quantities. So that's why I wrote here at the bottom, these quantities on our microscopic world are really measurable results in the macroscopic world of what's happening at the level of atoms and molecules. A huge term for us, it has already come up a couple of times, is energy. Right? We talked in one of the earlier slides about forms of energy, chemical energy, mechanical energy, and so on. As we start going into the details, we think of energy as, say, total energy. You can have the sum of all the possible energy modes in my macroscopic approach. We'll use, say, the symbol, capital letter E, to denote that energy. That energy would really be made up of different types of energies. So when I say this gas in the previous example, if I say this gas has energy, I can break down that energy into different types of energies. So by far the most important energy for us will be something that we call internal energy. Internal energy is in fact associated with those microscopic properties of the system that I mentioned up here, which we measure in our macroscopic view by means of, say, pressure and temperature. So a certain pressure and a certain temperature will be the reflection of molecular activity, and that represents a certain amount of energy that exists within my system. As I said, by far that will be the most important form of energy for us, the so-called internal energy, associated with the atomic molecular energies of the system. But we could have other forms of energy. So I wrote here a couple that are common in thermodynamics: kinetic energy and potential energy. And you're very familiar with those, so we don't need to spend a lot of time talking about those. Kinetic energy is, of course, the motion associated with the motion, with the velocity that the system has. You know, in this picture, again, it looks like the gas is nicely sitting there. It doesn't seem to be moving. But if I start moving the piston up and down, this gas is going to move. It's going to acquire some velocity that I can measure in the macroscopic world. And of course, that velocity will be associated with some kinetic energy. And this potential energy that you see here is actually gravitational potential energy. So the fact that if I take my cylinder and I move it up somewhere higher in the lab, I take it from a lower shell to a higher shell, it will have acquired some sort of gravitational potential energy because of the fact that I moved it up with respect to a gravitational energy system. Okay, any questions? Okay, let's keep marching along. Next concept. What are thermodynamic properties? What do you think are thermodynamic properties? Give me one example. Anything.
Entropy.
Getting help from here, getting fancy. Entropy. Right? Entropy. What else? Pressure. What else have I mentioned a moment ago? Energy. Mass. Temperature. Right? What are they? How would you define them then? What is another word that you could use for property in this case then? That would mean more or less the same thing.
Characteristics.
Huh?
Characteristics.
Very good. Characteristics that help describe the state of a system. So it's a characteristic that helps us describe the state of a system. And I underline the word state because, of course, that is another concept that we need to learn and use. So a characteristic that describes the state of a system is a thermodynamic property. When I say state here, I mean a thermodynamic state. So I underline state, thermodynamic state. It's a specific condition a system is in as determined by its properties. So it's kind of a circle definition, right? So the properties are the set of characteristics that define the state, and the state is the condition the system is in as determined by its properties. In other words, this is saying that if I have a certain values for the properties, those values of those properties will determine the state of that system. And a question that will be important for us later on is, well, how many properties do I need to know to determine the state of a system? How many do you think? How many properties, think of the gas in the cylinder again, how many properties would we need to know to uniquely determine the state of that gas, of that system? That's a question whose answer you shouldn't know, except for the fact that you may have seen some thermodynamics in physics or somewhere else. Any guess? 2, 3, 4? I won't answer that question today, but we'll get to that. This is similar to saying, well, how many properties do I need to define uniquely an individual in this class? This class is pretty large, so if we just say, for example, well, first name, right? And I just say Mike. How many Mikes? 1, 2, 3. So it's not enough, right? It's not enough. So I would have to throw in a last name. Most likely, if I put a last name, most likely, will be okay. Probably there will be a unique person for that first name and that last name, because this is a large group, but it's not a group that is, say, in the thousands. If we were in the thousands, that might not be enough. You might need middle name. You might need 3. So think about that in terms of the thermodynamic system. How many do we need? And we'll talk about that later when we come back to this topic. For now, just know what property is and what the thermodynamic state is. Here's another very important one. The concept of equilibrium. Or maybe I'll end it there after this. So equilibrium, it says there, a condition of balance characterized by the absence of driving potentials. That's kind of what you might say, well, what does that mean? So how would you define equilibrium with your own words? Let's try somebody on this side. Yeah, equilibrium. It's still in a thermodynamic sense, but with your own words.
External force equal internal force.
External forces equal internal forces. I'll give you some points for that, but anybody else? You can derive it from this definition, yes?
I would say lowest possible energy state.
Yeah, but now you're getting too fancy. How about a very plain?
Qn plus W.
Now you're getting fancy using symbols and equations. Plain word for somebody who is not an engineer, not in thermodynamics. You want to explain it to a friend who is not coming to school.
There's nothing driving the system.
Or nothing is happening. Nothing is happening. That's probably the simplest definition. Nothing is happening. That's equilibrium. So if nothing is happening, that's equilibrium. Of course, what she said is true. There is nothing forcing something to change. So it's kind of the same thing, right? Nothing forces something to change, then nothing happens. Give me an example of something that would break away from equilibrium in the properties that we've been talking about. The properties that we have discussed today, people have thrown properties around. Give me an example of something having to do with a property that would make something happen. Temperature, in what sense?
If you increase temperature, volume.
No, not exactly that. Hold on. Something with temperature. What do I need to do with temperatures for something to happen? Make them different, right? Have the temperature, say, on this side of the room higher than the temperature on that side of the room. What would happen? Heat will move from this side to that side, right? So that's an example. We'll pick it up on Thursday.